ओके बिस्मिल्लाहिर्रहमानिर्रहीम। तो आज हमारा सेकंड क्लास है ऑफ द क्वांटम मैकेनिक्स। तो कल कुछ स्टूडेंट्स ने मुझे मैसेज लिखा था कि हम लोग ज़्यादा इंग्लिश में यूज़ ना करें, इंग्लिश में इसको ज़्यादा डिमॉन्स्ट्रेट ना करें। सो आई विल ट्राई टू मेक इट सिंपल, यूज़ मोर अ बिट हिंदी, उर्दू एंड सम इंग्लिश, क्योंकि इसमें आप इंग्लिश को तो एस्केप नहीं कर सकते, बिकॉज इट इज़ एक्चुअली इट हैज़ बीन the research has been done in the English, and then it's a mathematical procedure, this quantum mechanics. तो मैं कोशिश करूँगा कि I will use less English and use language like Urdu and Hindi. Okay, तो आज का हमारा जो topic है as per your syllabus, that is time independent Schrodinger equation. So your topic is time independent Schrodinger equation। ये बहुत ही इंपॉर्टेंट इक्वेशन है क्वांटम मैकेनिक्स के। So time independent Schrodinger equation, टाइम इंडिपेंडेंट श्रोडिंगर इक्वेशन, ये आपका टॉपिक है। इसके साथ में लिखा हुआ सिलेबस पे, एंड मीनिंग ऑफ वेरियस टर्म्स, एंड मीनिंग ऑफ वेरियस टर्म्स। इसके साथ जो टर्म्स इसमें इन्वॉल्व है श्रोडिंगर इक्वेशन में, सो व्हाट्स एक्चुअली दैट। सो दिस इज आवर टॉपिक। सो विल ट्राई टू मूव, मैंने कल भी कहा था कि इतना ये बहुत ही वास्ट टॉपिक है, इसमें ह्यूज अमाउंट ऑफ मैथमेटिक्स इज इन्वॉल्वड। सो विल गो विद द बेसिक्स विच इज योर रिक्वायरमेंट। तो व्हाट एक्चुअली इज द श्रोडिंगर इक्वेशन? देखिए, हमने कहा था कि इन द क्वांटम मैकेनिक्स वी आर डीलिंग विद द सब एटॉमिक पार्टिकल्स। So we are basically dealing with subatomic particles. Subatomic particles means electrons, neutrons, protons, and so on. So we are basically dealing with microscopic particles, minute particles. Now, let us take an example that we have an electron which is present in the hydrogen atom. Hydrogen atom is atomic number 1. So when electron that's present in the hydrogen atom, so that means now we want to understand this electron. We want to understand how it behaves, what is the value of its energy, where it can be located. So we have to use the Schrodinger wave equation. अच्छा, दूसरा क्वेश्चन इसमें कि it's a time independent, इसका मतलब है टाइम डिपेंडेंट भी इक्वेशन होती है। So, but we have in our syllabus, it is time independent. That means वो Schrodinger equation where there is no involvement of time. So this, let us consider that the mass of this electron or mass of this particle is m, and now since it's present, electron will not be isolated. It's present in some in atom. So let us consider that this whole scenario with the help of a Cartesian coordinate system, a three-dimensional coordinate system. And our system is located, because obviously our system has x, y and z direction. So this is your x coordinate, this is your, let us say, z, and this is your y. And we'll assume that our electron is a mass m, or our particle is a mass m, and then it's actually moving along the x direction. So particle of mass m is moving along the x direction. लेकिन मैंने इसको in the form of wave क्यों दिखाया? जैसे मैंने कल भी कहा था कि as per the de Broglie relationship, wavelength is equivalent to h by mv. If a particle is moving with a velocity v, the wavelength is related to the mass by this formula. So that means if mass is less, or wave character is more. Since particles, they have these electrons, they have very less mass, very minute mass. That means its wave character is more. That's why I have shown this particle in the form of a wave. So it has a dual nature and its wave character is dominant. So now let's consider an electron, a particle electron, which has it's moving along the x direction. Fine. So that means we are trying to understand the energy, or we are trying to understand the motion of an electron along the x dimension. Okay. So what we need actually finally, that means we try to understand this electron. So this particle or this wave is expressed in terms of a function called as psi, P-S-I. So it's expressed in terms of function called as psi. So that means in the quantum mechanics, the state of system is expressed by a wave function. State of system, ये बहुत important है. A state of system is expressed by a function called as psi. So psi actually represents that particle, or we can also say that psi represents that electronic wave. So both one and the same thing, because it has a dual nature. Matter has a dual nature, even though being lesser in the mass has more wave character. So we can say psi represents that electronic wave, or psi represents that particle. So in order to understand this whole system, we have to understand that wave function. Okay? So, or we have treated that particle as a wave, or we have treated that particle a wave that is represented by a wave function called as psi. ठीक. अब इसी psi को हमें define करना है. इसी psi को we should get the value of this psi. ठीक. What is the value of this psi? In order to understand that value of psi, how can we get that value of psi? We need the Schrodinger wave equation. So ये तो हो गया basics about the Schrodinger wave equation. Now, what actually is the Schrodinger wave equation? Schrodinger wave equation के लिए एक derivation है. Derivation में point number 1 ये होता है कि we are considering a wave. We take a stationary wave, which is stationary, or a wave which is generated from a spring. उसकी equation को हम use कर लेते हैं, and as per that wave, as per the mathematics, जो wave की वो equation होती है vibrating spring की, that is that this wave function is equal to amplitude of the wave multiplied by sine of 2 pi x divided by the wavelength. एक इस रिलेशन का यूज कर लेते हैं. सेकंड, हम de Broglie's रिलेशनशिप का यूज कर लेते हैं. wavelength is equal to h Planck's constant divided by mass into velocity. तो दोनों equations की हेल्प से we actually derive the Schrodinger wave equation. आपकी बुक में है ये. I will not discuss this here. You try to do it. If you don't understand that, so please you can contact me. So इन दो equations को मिला के we are actually getting the Schrodinger wave equation. So that Schrodinger wave equation is basically, I will show it here. That is psi square. Sorry, it is psi square del square divided by del x square into your wave function plus 8 pi square m divided by h square into e minus v into psi is equal to 0. This is basically जो आप वहां से derive कर लेते हो. This is your Schrodinger wave equation. हम इसको ऐसे रीड कर लेते हैं. del square psi divided by del x square plus 8 pi square m divided by h square. This is bracket e minus v into 0. अब क्या है? What is this del square psi? Basically जो हम मैथमेटिक्स में पढ़ते हैं d by dx, that is differential of something, any function with respect to x. यहाँ पे this is the same thing. यहाँ पे partial differential, it is d by dou by, इसको dou भी बोलते हैं, del by del x. दैट्स द सेम del by del x। तो बेसिकली एक फंक्शन की डिफरेंशिएशन की गई है यहाँ पे। तो यहाँ पे हमारी फंक्शन क्या है, दैट इज वेव फंक्शन इज psi। सिंस आवर वेव फंक्शन इज psi, its value depends on the position x, so its value depends on position x। the same, its value depends on position x, so I can write that is del by del x into this psi। अब यहाँ पे ये जो टर्म है del square, ये psi जो है इट्स कॉल्ड डिफरेंशियल ऑफ x, उसको दोबारा डिफरेंशिएट किया गया है विथ रेस्पेक्ट टू del by del x। तो इसकी डिफरेंशिएशन जब हम दोबारा करेंगे into psi, so we'll end up with del square, del into del, that's del square psi divided by del x square। So this is basically called as the double differential। So basically Schrodinger wave equation is a double differential equation। So ये बहुत ही important है। So Schrodinger wave equation is a double differential equation। So it's a double differential equation। So double differentiation of the wave function x plus 8 pi square constant निकलता है। m is the mass of the particle, that's the mass of the electron, h is the Planck's constant, यहाँ पे h square है। And then we have, this is E represents the total energy and V is basically the potential energy of the system। And this is all about the Schrodinger wave equation when we are talking about an electron or a particle which is moving along the x direction। Now, जैसे हमने कहा था कि in any system we have the 3 dimensions। So if we use this for the 3 dimensions, then the Schrodinger wave equation becomes like this। So for 3 dimensions, Schrodinger wave equation becomes del square psi by del x square plus del square psi divided by del y square along the y direction, then del square psi divided by del z square। So instead of this we have to use del square psi divided by del y square, then plus del z square। So it becomes a Schrodinger wave equation along the 3 dimensions। So we can write it, so the Schrodinger wave equation along the 3 directions is like this: del square psi divided by del x square plus del square psi by del y square psi by del z square plus 8 pi square m by h square into E minus V psi is equals to, this is your Schrodinger wave equation along the 3 dimensions। इसी Schrodinger wave equation को solve करके we can understand the wave function, we can understand the energy of the wave function, what is the value of the wave function। So this is the time independent Schrodinger wave equation, that's the double differential of wave function with along the x direction, likely double differentiation along the y direction, double differentiation along the z direction। So overall the value is equal to 0। Now if we want this equation to be written in other form, we can write it this, ये जो term है this one, इसको हम replace कर सकते हैं by, we can write it, इसको हम replace कर सकते हैं by del square psi, where this del square which is equal to del, this is del square by dx square, del square by del y square and dz square, this is called as the Laplacian operator। So this is your Laplacian operator। So now थोड़ा सा पेज मूव कर लेते हैं। So this is your Laplacian operator। we can write our Schrodinger wave equation as del square psi plus 8 pi square m by h square E minus V, that's total energy minus potential energy of the system, multiplied by wave function is equal to 0. So this is other form of the Schrodinger wave equation. This is your Laplacian operator. Laplacian operator. There are many operators in quantum mechanics, लेकिन वहाँ discuss नहीं करेंगे. There's Hermitian operator also, Hamiltonian operator also, but this is your Laplacian operator, and this is other form of Schrodinger wave equation. Then we have now what is the potential energy? Now other term is potential energy. Potential energy is basically equivalent to ZE square minus ZE square by R, where Z is the atomic number of that particular chemical species. For example, in this case we had hydrogen atom, so Z is equal to 1. Or we can also say Z is basically it is basically minus ZE multiplied by E. So this Z is the charge on the nucleus, and minus is basically, it means the system is bound. It doesn't mean the sign. It means the system is bound, its value is taken to be negative. So it's basically ZE, that's the charge on the hydrogen atom. That is the charge in the nucleus of the hydrogen atom, and E is the electronic charge. So one charge of nucleus multiplied with the charge of electron divided by the distance between them. Let us say it is located at some finite distance. Electron is located here, so this distance is R. So the energy of this system, that is the potential energy, that is equal to ZE square by R minus sign, that means system is bound. We use minus sign for that. So this is the potential energy. So likely ये जो Schrodinger wave equation है, it is useful for single electron systems, single electronic systems like hydrogen, helium plus, lithium 2 plus, boron 3 plus, and so on. Boron 3 plus and so on. If it is a multi-electronic system, for multi-electronic system this equation doesn't hold as good. So it doesn't hold as good for multi-electronic systems. Multi-electronic systems. For multi-electronic systems we have to use some approximations, and those are very complicated. They are not at this level, so we will not discuss those. So we use approximations in order to understand the wave function here. So this is all about the basics of the Schrodinger wave equation. अब इसमें सब कुछ last कुछ important चीजें बची है कि that this ये जो value of psi है, जो wave function है, wave functions के कुछ values हमें निकलते हैं Schrodinger wave equation से. All the values of the wave function are not acceptable. Only those values are acceptable which are finite. So only those values of wave function are acceptable which are finite. Second, and there should be always a single value for psi, single value. There should be single value along all the x, y, and z coordinates. The value of psi should always come out as single value, and that value should be finite, and then psi should be continuous. Continuous, you know that in the waves, the concept of waves, एक होता है continuously, this is called continuous form, and second is discontinuous. You see that it's broken, or you see it's a half wave, then it is discontinuous. So it should be continuous. So only those values are acceptable which are continuous, single values, and finite value should be there, and overall value of the wave should be, that should come out to be 1. That means overall पूरे space में, पूरे along the 3 dimension में, the value of psi is equal to 1. This concept where we say that psi should be the value of psi should be equal to 1, this is called as normalization condition. It's called as normalization. Or we say that this wave function is normalized. that's probability of its finding along whole space is equivalent to 1. इसके अलावा जैसे मैंने कहा था, since an electron cannot be isolated from the nucleus, so it is always present somewhere closer to the nucleus at some specific distance, at certain distance, and that distance is very, very less, obviously. So that means if we consider that it is present beyond that particular distance, we say that the value of psi is 0, or we say that the value of psi, so fifth point, the value of psi at infinity is 0. At infinity, that is 0. इसका मतलब ये है कि आपका जो एटम है वो बहुत लार्जर साइज का है. So now it is no more a quantum mechanics, that becomes a classical mechanics. So the value of psi should not be 0. That's it. The value of psi should be it should be finite, very minute values. And if the value of psi is coming 0, and that is 0 only possible at the infinity, we say that now it's basically a macroscopic system. It's a classical mechanics, it's not a quantum mechanics. So this is all about the basics of the Schrodinger wave equation, and इसमें जो terms involved है, those I have discussed. So what is the output finally? That what we get from Schrodinger wave equation, we understand this wave function, and then we can calculate the energy. क्योंकि ये सारी चीजें इस लेवल पे नहीं है, so I am not discussing this here. So we can calculate the energy with the help of Schrodinger wave equation, energy of the electron, particularly when it is a uni-electron system. We can calculate the energy, and we can also calculate the position. So we can calculate the position. We can actually know the probability of finding the electron, where electron is located around the nucleus. So we can understand the probability of finding the electron around the nucleus. So these we can get from the Schrodinger wave equation, considering our electron as a wave, or considering our electron as a wave function. Okay? And then only though this, we can only calculate these values when we say that when our wave function is a value which is finite, and at infinity the value is 0, and that wave function is single valued, it is continuous, and it is normalized. So this is all about the basics of the Schrodinger wave equation and some of the crucial terms which are involved in it. तो इसमें अगर कोई question है, you can also try the derivation from the book. उसमें हम basically वो standing wave equation और de Broglie's equation को मिला के निकाल लेते हैं. ज़्यादा tough mathematics नहीं है, simple mathematics है वो. So this is your Laplacian operator. So if you have still some confusions, you can contact me back. So we'll try to solve it. So this is all for the day.